Okay, ladies and gentlemen, we are going to talk about polynomials, and this is Polynomials in Practice Day 1. So we're going to start with a technical definition of a polynomial, and don't get too confused, it's not too bad. So for a polynomial, we'll say it's a sub n times x to the n. And again, this is a polynomial in 1 degree. So a is a constant, and then these are the highest powers. And then we're going to go down to lower powers, a sub n minus 1 times x to the n minus 1. And then we might have some spaces in between. And then we're going to say this is a to the first, x to the first. And plus maybe some constant a. And then this is where n is a whole number. So that seems a little bit confusing, but we're going to look at some examples. So in this example, we have negative 5.4 times x to the fourth plus 13x squared plus 2. So my leading coefficient is negative 5.4. My degree is the highest power, so the number in the highest power. So we see x to the fourth as the highest power. So we could say this is degree 4. My terms, each of the pieces here are terms. So we have negative 5.4, x to the fourth is one term. I'm going to put a comma, 13x squared, and then a 2. So these individual pieces, taking away the adding or subtracting sign, are the terms, and then our constant is 2. So the degree of the polynomial, what that is the highest power. And what that tells us, in a graph, it's going to tell us the maximum number of times the graph crosses the x-intercept, or the graph crosses the x-axis. So this tells us the maximum number of x-intercepts. And then the y-intercept is just where the graph crosses the y-axis. And note, this is when x equals 0. And then just a note on the exponents, they must be whole numbers. So we looked at an example of a polynomial. I'll do a couple non-examples. So if I did y equals 5, x to the 4.5 plus 13x squared plus 2. Why this is a non-example, I have a decimal in the exponent. So I'm just going to write decimal exponent. Another example, let's say I said y equals 5x to the 6 plus x to the fourth over 2 plus 6 over x. Now, in looking at this, I have a coefficient and an integer or a whole number exponent. Here, this looks like it has a fractional exponent, but 4 over 2 actually equals 2, so that's okay. But here, I could rewrite 6 over x as 6 times x to the negative 1. So this has an exponent that is not a whole number. So you can't have a negative exponent. So for our next activity, we were asked to star the polynomials. So if I look here, this is a polynomial. So I'm going to just put a star. This is not. So it equals 3 times x to the negative 1. So I'm just going to put a little drawing there and write negative exponent. This is a polynomial. So I'm going to put a star. This 4 over 2 ends up being 2, so it is a polynomial. This is not. I notice the variable is lifted and in the exponent. So the reason this is not a polynomial is the variable is in the exponent. And then in looking here, this is a decimal exponent, so not a polynomial. Here, everything checks out. So we have coefficients. The powers of x are all whole numbers. So it is a polynomial. Here we have a radical sign. And just a reminder, this would equal 9 times x. The radical is to the 1/2 power plus 2x. So the rule there that it's breaking is I have a fraction for an exponent. Looking at 3x to the negative 2 plus x plus 7, again, I have a negative exponent. Here, the 12 is a whole number. So this actually is a polynomial. You can just have a constant. I could rewrite this with a variable, and I could say this is 12 times x to the 0 power. So you see I have a variable with a whole number exponent. So I'd like for you now to try practice problem 1, A and B. And then also here, C, D, A, B, C, and D. So we'll check those in class. So now we're going to look at the finite differences for finding the degree of polynomials from a table. So mathematicians didn't always have graphs, so they couldn't find where the graph crossed the x-axis. So oftentimes if they had information in tables, they looked for connections amongst the table to find what the degree is. So in this first table, as I look at that, x is just counting by ones, and the y number is counting up by threes. So if I express that here as the differences, I'm going to write plus 3. 13 to 16, I add 3. I add 3. I add 3. And I add 3. So if I look here, I can see the first difference is constant, which means this is a degree 1 polynomial. And we can actually say if it's a degree 1 polynomial, we can just say it's linear. So sometimes it's not that easy. So we see in the next problem, x is counting up by 0.1, and the y numbers are counting up by a different amount. So if I find my difference here, I can go 2.88 minus 1.88, which is I'm adding 1. And then here, 3.92 minus 2.88. You can use a calculator if you need to. And I see that I'm adding 1.04. And then 5 minus 3.92 gives me 1.08. And then 6.12 minus 5 gives me 1.12. And then 7.28 minus 6.12 gives me 1.16. And then over here, I need to go on because the first difference is not constant. So I look and find the second difference. So 1.04 minus 1 is 0.04. And again here, 1.08 minus 1.04 is 0.04. 1.12 minus 1.08 is 0.04. And then again, another 0.04. So we can see here that the second difference is constant. So in looking at this, this is a second degree polynomial. So now we're going to have a graph where the x number is counting up by 5s, but the y values go in a little bit of a different direction. So what I'm going to do is calculate these differences. And I have -5, but I'm subtracting -57.5. So I know that when I subtract a negative, I add. So I go -5 plus 57.5. And it's 52.5. And then here, -2.5 minus -5. So I'm going to add 5. And then that gives me 2.5. And then here, 25 minus a negative. So I'm going to add 2.5 or minus -2.5. And then I'm going to add those two numbers and get 27.5. Then I'm going to keep going. 152.5 minus 25 gives me 127.5. And then here, 455 minus 152.5, I got 302.5. And then I notice the first difference is not constant. So I'm going to go and calculate the second difference. So 2.5 minus 52.5, I can do that. It's -50. 27.5 minus 2.5 is positive 25. 127.5 minus 27.5, I'm adding 100. 302.5 minus 127.5 is 175. And then from there, ladies and gentlemen, we can keep going. 25 minus -50 is 75. 100 minus 25, 75. And 175 minus 100 is 75. So we see the third difference is constant. So this is a third degree polynomial. Okay, so complete the rest of the questions.